Welcome back to Linear Algebra. I'm Dr. Jeff Groh. Today, we're going to talk about singular value decompositions. As you know, if a matrix is diagonalizable, it can be expressed as an invertible matrix P times a diagonal matrix D times P inverse. Also, if the matrix is symmetric, then we can go further. There is an orthogonal matrix Q, a diagonal matrix D, and you can multiply by Q transpose because the transpose is the inverse for an orthogonal matrix. Now we're going to suppose that A is an element of the vector space of M by N matrices. Not only is this going to be perhaps non-singular, it's not even going to be square, and we're going to see what we can do with that. If A is M by N, let's look at A transpose A. A transpose will be N by M, where A is M by N. Since the inner values match, product is defined, and you get an N by N matrix. Something that's square. But you get something that's better. When you take the transpose of A transpose A, the transpose reverses the order of the product. And the transpose of the transpose is the original matrix, which implies that A transpose A is symmetric. That comes loaded with a lot of information. In particular, since it is symmetric, its eigenvalues are all real. Not only are the eigenvalues of A transpose A real, they're non-negative. Note that X transpose A transpose times AX is in fact AX transpose AX. Well, isn't that the norm of AX squared? And that has to be greater than or equal to 0. If X is an eigenvector of A transpose A, and let's suppose that X is not the 0 vector, what happens then? X times A transpose AX will be X transpose lambda X. The lambda comes out, you get X transpose X. And that too is lambda times the norm of X squared. Now we've already shown that this quantity is non-negative. The norm of X is non-negative, which implies that lambda is also non-negative. What we're really after is something resembling eigenvalues of A, but A won't have eigenvalues because A is not even square. What we'll do is we'll make the following definition. Set sigma sub k to be the principal square root of these eigenvalues lambda k. These are going to be called singular values. the singular values of a non-square matrix are the principal square roots, the non-negative square roots, of the eigenvalues of A transpose A. It is customary that we organize these in a way which is from greatest to smallest. We're going to go down to sigma sub r, and then after that, all of the others are 0. So down to sigma sub r, which is the smallest positive singular value, and then all the others are 0. We've already seen a portion of the proof of the following theorem. A, B, m by n. Suppose that B, V1 through Vn, is an orthonormal basis of eigenvectors for the square matrix A transpose A. We know that such a basis exists by our study of symmetric diagonalization, and this is a symmetric matrix. With corresponding eigenvalues, lambda 1 through lambda n. Sigma sub k is, of course, the principal square root of lambda sub k. Then, first off, the norm of AVK is sigma k, and AVI will be orthogonal to AVJ, so long, of course, that I does not equal j. The proof is fairly trivial. It goes pretty much like you might think. Remember that the norm is the square root of the dot product of the vector with itself. And the Euclidean dot product is just U transpose V. And that's the square root of VK transpose A transpose AV. Now remember, VK is an eigenvector of A transpose A. So we're going to get the square root of VKT times lambda VK. Remember that we can separate this into the square root of lambda k times the square root of VK transpose VK, which is the norm of VK. Now, by assumption, the VKs formed an orthonormal basis. And because it was an orthonormal basis, all of these norms are 1. And, what is more, the square root of the eigenvalues are the singular values. That's the proof of the first part. Now for the second part. To prove the orthogonality of AVI and AVJ requires taking the Euclidean dot product. Now, the dot product is transpose, remember, AVI transpose AVJ, and that gives us VI transpose A transpose AVJ. Now, keep in mind, these V's are eigenvectors for A transpose A. So we'll get lambda J Vj out of that. The lambda j is a scalar. Scalars commute with everything. And we end up with Vi dot Vj. But wait a minute. These V's are supposed to form an orthonormal basis to Rn, which means if I is not equal to j, you get a zero scalar here. It'll be 1 if they're equal, but 0 if they're not, because they are orthogonal. And that shows that A maps this orthonormal basis of vectors v sub k onto something that is at least orthogonal. It may not be orthonormal because they may not be normalized. Some of these might be the zero vector. However, if we limit ourselves to the non-zero cases, we will get a basis. Let A be an M by N matrix. Suppose we have an orthonormal basis of Rn consisting of eigenvectors of A transpose A, where for the eigenvalues, lambda 1 is greater than or equal to lambda 2. We have this all the way down to lambda r. That's going to be greater than lambda r plus 1. All the remaining ones will be 0. Then if we set B prime to be equal to AV1 over sigma 1, AVR over sigma r, then this collection, being normalized by dividing by these sigmas, is an orthonormal basis for the column space of A, and the rank of A is R. Suppose W is in the column space of A. Then W is in the range of the linear transformation defined by A. That means there exists some vector V in Rn such that AV is W. Since B, which is our orthonormal basis V1 through Vn, is a basis, there exists C1 through Cn, so that V is C1 V1 plus all the way down to C and Vn. Which implies then, if we take A times V, we'll get C1 AV1. Now some of these are going to be zeros, because after little r, we'll have CR AVR, all the rest are going to be zeros. So we can forget about those. And then you see W must in fact be a linear combination of AV1 through AVR. That implies W is in the span of AV1 over sigma 1 through AVR over sigma r. So anything in the column space is in the span of these. What we need to show then, to show that these form a basis for the column space, is to show that they are linearly independent. But they have to be. They're orthogonal to each other. These are pairwise orthogonal. And since they're normalized, they're non-zero. They are linearly independent. Therefore, AV1 over sigma 1 through AVR over sigma r is an orthonormal basis for the column space of A. You can also see that the rank of A must be R then. It's here where we make the theorem on the singular value decomposition. Let A be m by n. B is going to be V1 through Vn, an orthonormal basis of Rn consisting of eigenvectors of A transpose A with corresponding eigenvalues lambda 1 through lambda n. We are, of course, going to arrange these so that lambda 1 is greater than or equal to lambda 2, greater than or equal to lambda r, which is strictly greater than lambda r plus 1, which is lambda n, which is 0. So the last few are all 0. We will, of course, set sigma 1 to be the square root of lambda 1, the principal square root, through sigma r. Then, now here's the singular value decomposition. A is going to be some matrix U times some matrix sigma times some matrix V transpose. I have to tell you where we get all of these different matrices. For the matrix sigma, it's going to be as close to diagonal as you can get for a non-square matrix. It's going to have a block structure where in the first block you get the singular values down a diagonal. Everything else in this matrix will be 0. V is going to be the matrix consisting of this orthonormal basis for Rn consisting of eigenvectors. We have yet only to describe the matrix U. The only thing we haven't defined is the matrix U. And to do that, I'm going to set U1 to be AV1 over sigma 1. That's going to work until we get to sigma r. But what do you do after that? These vectors are in Rm. R is less than or equal to Rm. we're going to extend U1 to UM to obtain an orthonormal basis for Rm, and then of course we'll set U to be U1 through UM. Since the columns of U are an orthonormal basis for Rm, and this was an M by M matrix, this will in fact be an orthogonal matrix, so that U transpose U is the identity. We want to show that A can be expressed as U sigma V transpose. This is equivalent to showing a V equals U sigma V transpose V, and since V is a matrix formed by putting an orthonormal basis down the columns, then it is an orthogonal matrix. You get the identity here. So it is enough to show that AV is U sigma. Let's look at AV. This is going to be AV1 through AVN. Now these are related to the U's. Remember that U1 was AV1 over sigma 1. So here we're going to get sigma 1 times U1. That's going to work at least until we get to sigma R UR, but what happens after that? Well, all the other sigmas are 0. So we can call that just a bunch of zeros all the way to the end. So now, what happens when we look at the other side? We're going to have these U1s, or UM, and we're going to have sigma 1 through sigma R, and then everybody else is a 0 in every other position. When you multiply such a matrix, what you'll end up with is sigma 1 U1, at least through sigma R UR, and then everything else zeros. These two are equal, and so the theorem is over. I'd like to develop the theory just a little bit more beyond this, but first we need an example. Suppose A is the matrix 1, 1, 0, 1, 0, 1. About as simple as an example as you can dream up. Let's look at A transpose A. To get the transpose, remember, you switch the roles of rows and columns. Let's see, we'll get 2, 1, 1, and 2. Note that this is symmetric. Now, what are its eigenvalues? We'll have 2 minus lambda, 1, 1, 2 minus lambda. That's 2 minus lambda squared minus 1, or lambda squared minus 4 lambda, and then plus 4 minus 1 is plus 3. This factors as lambda minus 3, lambda minus 1. So we get 1 and 3. The singular values, remember, must be in descending order. Will be square root of 3 and 1. So at least we know the singular values. Next, we find the eigenvectors. Those are easy to find. For lambda equals 1, we can find, I'll call it W1, because it won't be necessarily normalized. You can see right off that 1 minus 1 gives you an eigenvector in that case. For lambda equals 3, 1, 1 will do. To normalize these, they both have norm equal to the square root of 2. So we're going to have, for v1, that's over here, 1 over root 2, 1 over root 2, and for v2, we'll have 1 over root 2 minus 1 over root 2. Then, how do we obtain the vectors this gives us v is 1 over root 2, 1 over root 2, 1 over root 2, negative 1 over root 2, or just 1 over root 2 times 1, 1, 1 minus 1. Now we need to obtain the u's, which correspond to these, by multiplying by a and dividing by the singular values. So u1 should be av1 over the square root of 3. That's 1 over root 3 times 1, 1, 0, 1, 0, 1 times v1, which we'll write as 1 over root 2 times 1, 1. That'll give us a 1 over root 6. We'll have 2, 1, 1. That's u1, and now we need u2. That's going to be 1, 1, 0, 1, 0, 1 times 1 over root 2 times 1 minus 1. That's going to give you 0. We'll have 1 over root 2 out front. 1 minus 1. We have u1. We have u2. We need to extend this to a basis for R3. We're missing a vector. We need something that is orthogonal to each of these. We want to obtain an orthonormal basis. To obtain this u3, let's take the cross product of two of these vectors. Let's take 2, 1, 1 and find the cross product of 0, 1, minus 1. Whatever we end up with, we'll just normalize it later. We'll have 2, 1, 1, 0, 1, minus 1. That gives us the vector minus 2. We'll have negative 2, but that gets the sign switched, and then 2. So I'm going to replace this with just the vector minus 1, 1, 1, and then normalize that because it's easier to do in my head. So the norm here is the square root of 3, so I'm going to choose u3 to be 1 over the square root of 3 times negative 1, 1, 1. This will then complete an orthonormal basis for R3, and then we can construct the matrix U. The matrix U is 2 over the square root of 6, 1 over the square root of 6, 1 over the square root of 6, and then 0, 1 over the square root of 2, negative 1 over the square root of 2, and then finally negative 1 over the square root of 3, 1 over the square root of 3, 1 over the square root of 3. An orthogonal matrix U. So we have an orthogonal matrix V and an orthogonal matrix U. Let's check that the theory works out. Let's remember that V is 1 over root 2, 1, 1, 1 minus 1. The matrix sigma will be root 3, 0, 0, 1, 0, 0. We need to verify that A, the original matrix, is U sigma V transpose. There's the question. U sigma root 3, 0, 0, 0, 1, 0 times V transpose, that's 1 over the square root of 2, times 1, 1, 1, negative 1. It's transpose being equal to itself. And so we'll have this 1 over root 2 out front. What do we end up with? Root 3, root 3, and then 1, negative 1, followed by 0, 0. We need to only multiply on the left by this matrix U. I'll move the 1 over the square root of 2 out front. And then put root 3, 1 minus 1, 0, 0. Let's see how this goes. When we multiply, we're going to have 2 over the square root of 6 times the square root of 3, and we have a 1 over the square root of 2. What is that? Well, root 6 is root 3, root 2. We'll have 2 over root 2 times root 2, that's just 1. Multiplying again, we'll get the same thing, 1. Then, multiplying, we'll get root 3 over root 6 here, plus 1 over root 2, all times this 1 over root 2. Well, how much is that? That gives us 2 of the same thing. 2 root 3 over root 6, which is root 3 root 2, 1 over root 2. We end up with 1 yet again. What happens when we multiply next? We'll have a subtraction between these identical terms. And that gives us 0. Down here, we get subtraction of identical terms, giving 0, and when we multiply again, that turns this into a plus. And once more, we get 1, and that is, in fact, A, and that checks the theory. To review, for the singular value decomposition, if A is m by m, there exists orthogonal matrices U, which is m by m, and V, which is n by n, such that A is U sigma V transpose, where sigma is these singular values, and then zeros everywhere else. Now we can get a little more mileage out of this by looking at the following. This matrix U, what were its columns? Weren't there AV1 over sigma 1, AVR over sigma R, and then maybe some zero. And then we filled out the rest to obtain an orthogonal basis. When we multiply by sigma, though, these won't matter. They'll all hit zeros. And these will hit the appropriate sigmas. And then we're multiplying by V transpose. V transpose has these V1 transpose in the first row, V2 transpose in the second row, and then when we multiply, we'll end up with the following sum. AV1 V1 transpose plus AV2 V2 transpose. And we only need to go up to AVR VR transpose because everything else hits a 0. This gives us another decomposition because these are outer products. These are all singular matrices of rank 1. Rank 1, all the way out to rank 1 are of those. Since the sum has to be rank R, since A has rank R, these will each add some new rank. It's like decomposing this according to independent rank matrices. That allows us then to rewrite A, maybe even approximate A, by truncating the sum at some finite part. Let's suppose A is M by N, non-square matrix representing the grayscale color levels in a black and white photograph. The matrix doesn't need to be square. In fact, most photographs are not square. And each entry will be the color level on the grayscale for a particular pixel in the photograph. Then we can decompose that photograph and maybe approximate the photograph by summing up to some truncated value. This allows us then to perhaps compress the image a little bit and save on some of the storage, perhaps. Or I was going to actually do an example like this, but I couldn't get the software in time for this lecture. So there is a nice example in your textbook that you can look up, and there are some nice examples online with the actual code necessary in order to produce these approximations to images. It's pretty cool. I suggest you check it out online.